Okay, so let's talk about enthalpy changes as it relates to the stoichiometry of reactions. So, of course, we know what is involved when we write a balanced equation. It gives you the relative amounts of the different substances involved in the reaction. Now, when it comes to delta H in these types of calculations, a couple of things you need to remember. One, when delta H is negative, it means that reaction is exothermic, right? If delta H is positive, that means that the reaction is endothermic. But we can also look at it in terms of delta H, or the amount of heat involved, as being thought of as either a product or a reactant. Now, of course, they are not actually products and reactants in the same sense as other substances, right? But we can treat it as such for the sake of solving problems. So in the case of an exothermic reaction, then the heat that is produced can be thought of as a reaction product. And if the reaction is endothermic, that means that the heat that is absorbed can be thought of as a reactant of the reaction. And therefore, based on that, we can actually produce conversion factors which involves these heat changes. So for example, if you look at this reaction between hydrogen and chlorine to form hydrogen chloride, and the enthalpy change of that reaction is given as minus 184.6 kilojoules, then we can also write down conversion factors which involves this and any of the coefficients of these different substances in a balanced equation. So for example, one can write down the relationship between the enthalpy value and the moles of hydrogen, right? As shown here. You can do the same thing for chlorine. You can also do the same thing for hydrogen chloride. So we can basically treat the enthalpy change as a product or reactant, depending on whether or not the reaction is exothermic or endothermic, and treat it quantitatively in that fashion. So let's look at this example here, just to illustrate that point. They gave you the balanced equation, and they gave you the enthalpy change, and the question says that you have 5.67 moles of HCl that is produced. So the question is asking, what is the enthalpy change associated with this reaction? So the way I would set this up is that I would start off with the 5.67 moles of HCl, and I would multiply that by 1 mole of HCl above and minus 184.6 kilojoules below. Actually, this should be 2 moles of HCl below here, 2 moles of HCl down here. So that this unit and this unit will cancel out, and do our number crunching. And according to my calculation, I got, when rounded off to 3 sig figs, I got minus 1050 kilojoules as the answer. And that's basically how that is done. All right. So that's a relatively simple example to illustrate the stoichiometric relationship between the enthalpy change and the moles of a substance involved in a chemical reaction. Okay, so this brings us now to the whole area of calorimetry, which is basically studying how heat flow occurs in processes, chemical reactions and other processes, right? And the instrument that is used for this purpose is known as a calorimeter. And the one that you see here on the screen is of the low-tech variety, consists of 2 styrofoam cups, a cover with 2 holes. Let me go back to the pointer here. A cover with 2 holes. Through one of them, you're going to put a thermometer in. The other one, you'll put a stirrer in. And you'll have your reaction taking place in this styrofoam cup. And basically, let's say, for example, if the reaction is exothermic, then you'll see the temperature rise indicated in a thermometer, and then you can do some calculations to determine the enthalpy change of the reaction. Of course, you'd have to know certain specifics For example, you have to know the amounts of the substances involved and so on. Now, a special type of calorimeter is used as far as combustion reactions are concerned, right? Because combustion reactions involves the evolution of a relatively large amount of heat, right? And the type of calorimeter that we use here is called a bomb calorimeter, which is specially designed to withstand heat changes and so on. So we could not do this process in this ordinary low-tech calorimeter here because the heat changes will be too great and therefore will melt the styrofoam cup. So in this case here, what we have here is a steel encased bomb right here. Whoops, I'm sorry. You have your sample that you're trying to burn. So this would be your organic material. You have two wires, two fuses that leads into the sample right here. The bomb is basically immersed in a larger vessel which contains water. You have your thermometer here and you have your stirrer here just to make sure that when the heat is produced from this reaction, it's transferred to the water and uniformly distributed in the water so that you can record the accurate temperature. And again, you're going to need certain specifics, the amount of material, the amount of water that is used, the temperature changes, etc., to calculate the enthalpy change occurring when you have the combustion of that particular substance. So those are just two examples of calorimeters that are used to make measurements of heat flow. Okay, so since we're in the area of calorimetry, then we need to talk about some other terms. Now, whenever you're doing this sort of experiment, the key thing you need to remember is in the first line right here. Any heat that is involved, or I should say evolved in a reaction, is absorbed by the calorimeter, right? So what that means basically, just to simplify it in the form of an equation, is that Q reaction, the heat change of the reaction here, Q reaction is equal to minus Q of the calorimeter. Very important, right? So if the reaction is, let's say, exothermic, right? That means that the reaction is producing heat, then that means that the calorimeter will be absorbing the heat. On the other hand, if the reaction is endothermic, in other words, absorbing heat, that means that the calorimeter will be producing or would be giving heat to the system, all right? So that's very important for you to understand. Okay, so in the calorimeter, what we try to do is measure the temperature change that is occurring in the water, in the case of the bomb calorimeter, or in a solution, to determine whether or not heat is absorbed or evolved by a reaction. So therefore, if the temperature increases, let me just squeeze that in here. If the temperature increases, that means that Q of the reaction is negative, right? Because if the temperature increases, that means that the calorimeter is absorbing heat, which means that the reaction is producing heat. If the temperature decreases in this process, then Q of the reaction will be positive, all right? So these are just some key things you need to remember when it comes to calorimetry. Okay, some definition here. The heat capacity of a system is the amount of heat required to change the temperature of the system by 1 degree Celsius or 1 Kelvin. And we can represent it mathematically using this equation. Q, go back to the pointer. Q is equal to, C is equal to Q divided by delta T. So C is the heat capacity, Q would be the amount of heat change, and delta T would be the temperature change, right? So the units of C in this case, and I should specify uppercase C, is joules per degree Celsius, all right? Then we have what is known as a molar heat capacity. Now, to be honest, I don't anticipate us using this particular definition or applying this to any problem-solving exercises, but I'll just explain what it is. It is a heat capacity of 1 mole of a substance. And then we get to the specific heat, which is symbolized by lowercase c, which is the heat capacity of 1 gram of a pure substance or of a homogeneous mixture, all right? So the relationship between lowercase c, which is the heat capacity, which is the specific heat, and uppercase c, which is the heat capacity, is lowercase c is equal to uppercase c divided by m, which is equal to q over m times delta t. All right, so what we did here is basically substitute for c, q over delta t, and we end up with this equation here. Or another way of expressing it, which is a more common way of expressing the relationship, is given by this relationship right here. Hold on, let me do this here. I'm sorry. Which is given by this relationship right here. Whoops. Q is equal to C times M times delta T, where C is given in joules per gram degree Celsius. In fact, let me write that down here. So the units of C would be joules per gram degree Celsius. M is in grams, and delta T is in degrees Celsius or Kelvin. And it doesn't matter which one you use, numerically the results would still be the same in terms of the C, all right? Okay, so based on what we have just learned, we could do problems such as this one right here. This question says calculate the heat capacity of an aluminum block. Hold on, let me see. Okay. Calculate the heat capacity of an aluminum block that absorbs 629 joules of heat from its surroundings in order for its temperature to rise from 22 degrees Celsius to 145 degrees Celsius. So we're going to use Q is equal to M times C times delta T, right? Delta T. So the question is asking for C. So I would rearrange this to get C is equal to Q divided by M times delta T. And Q is 629 joules. Now remember, it says absorbs 629 joules of heat. So that means that Q is positive. So this will be plus 629 joules of heat divided by M. Oh, by the way, I just made an error. I just realized I made an error. Let me see if I can clear this up. Okay. The question did not ask for specific heat. The question asked for the heat capacity. So the equation that we're going to use instead would be C, uppercase C is equal to Q divided by delta T, all right? So basically, we just put the numbers in. Now Q is still going to be 629 joules, and delta T would be the change in temperature, and the change in temperature will be the final temperature minus the initial. That's basically what we do in all cases. Let me squeeze that up here. Any change in temperature will be the final temperature minus the initial temperature, all right? So in this case, it's going to be 145 degrees Celsius minus 22 degrees Celsius. And let me do my calculation here. So 629 divided by 145 minus 22. And then according to my calculations, this works out to be equal to 5.11 joules per degrees Celsius. All right, so that's basically how that problem is solved. Okay, some more things on specific heat. Now remember, this is the relationship between heat change, mass, specific heat, and the change in temperature, all right? So if delta T is positive, that means that Q is positive, right? Which makes sense. If Q is positive, that means that heat is absorbed. When heat is absorbed by a substance, the temperature changes would be positive, right? So that makes sense. And therefore, conversely, if delta T is negative, then Q would be negative because, of course, when a system loses heat, the temperature falls. So therefore, delta T will be negative, all right? Now, there are other units of energy apart from the joule unit. You have what is known as the calorie unit, which is not a metric unit, but it is still used to some extent. And the relationship between the joule unit and the calorie unit is given right here. It is 4.184 joules equals to 1 calorie. So you don't need to memorize this because, of course, this would be provided in the packet that I have made available to you in Canvas and that you'll have access to in your future tests. All right. There's also another calorie unit which is used by a nutritionist known as a food calorie, which is symbolized by these two symbols right here. Let me just go back to the pen or the pointer. So this is the food calorie unit, uppercase CAL or kilocalorie, which is equal to 1,000 of the calories here. All right. Okay, and what you'll find is that different substances will have different specific heat. Specific heat is basically a physical property, a quantitative physical property, you know, like density and melting points and freezing points and so on, right? And when it comes to the different types of substances, you'll find that there are certain trends that will become obvious. For example, you'll notice that metals typically will have very low specific heats. So as you can see here, metals tend to have specific heats less than 1 joule per gram degree Celsius. Water, on the other hand, has basically the highest specific heats, with a few exceptions. And this is due to a phenomenon known as hydrogen bonding, which we'll get to later on. All right. Okay. So let's apply what we have just learned to solving this problem. So this question says, how much heat in joules and in kilojoules does it take to raise the temperature of 225 grams of water from 25 degrees Celsius to 100 degrees Celsius? So this one is basically a straightforward application of the specific heat equation, which is, of course, Q is equal to M times C times delta T. So all we have to do is plug the numbers in. Now, in this case, you are not given the specific heat of water in the question directly, but that would have to be given to you in a test situation. And according to the table, the specific heat of water is 4.180 joules per gram degree Celsius. So let me just put the numbers in. So in the case of the mass, that would be 225 grams times 4.180 joules per gram degree Celsius times the change in temperature, which is 100.0 degrees Celsius minus 25.0 degrees Celsius. Remember, the change in temperature is always the final temperature minus the initial temperature. And in that case, that means that Q would be positive, as you're going to see down here. So 100 minus 25 gives you 75, multiplied by 4.180 times 225. And according to my calculations, when you round that off to 3 sig figs, let me do this again. 75 times 4.18 times 225. Okay, so based on my calculation, this works out to be 7.05. 7.05 times 10 to the 4. 10 to the 4 joules. And the question asks for you to convert it to kilojoules as well. So to do that, we have to multiply by a conversion factor. Remember, kilo means 1,000. So therefore, 1 kilojoule will go up here. 1,000 joules will go below. So the joule units cancel out here and here. So when you divide by 1,000, your answer becomes 70.5 kilojoules. So this becomes 70.5 kilojoules. And that's basically how that is done. All right. Okay. Let me do this last example here for this particular video, and then I'll stop and take a break and then do another video try to complete this chapter. So in this question, now this one is very tricky because you have to look at how this question is worded. It says, what will be the final temperature if a 5.0 gram silver ring at 37 degrees Celsius gives off, let me underline that, gives off 25 joules of heat to its surroundings. And it says use the specific heat of silver listed in the previous table. So let me go back to the previous table. Silver, where is silver? Okay, so silver has a value of 0.235. So let me write that down before I forget. So the specific heat of silver is 0.235 joules per gram degree Celsius. All right? Okay. Now, basically what this question is asking for the final temperature. They gave you the initial temperature, which is right here. They gave you the amount of heat that is given off, and it's asking for the final temperature, right? So what I would do is start off with Q is equal to M times C times delta T, right? What I would do is try to find the change in temperature, all right? Once I find the change in temperature, I will add it to the initial temperature to get the final temperature. So what I'll do is rearrange this to get delta T is equal to Q divided by M times C. Okay, so Q is equal to 25.0 joules divided by M, which is 5.00 grams, times the specific heat, which is 0.235 joules over gram degrees Celsius, all right? So let me do that calculation down here. So 25 divided by 5 times 0.235. Okay, so according to my calculation, when rounded off to 3 sig figs, this gives 21.2. Now, one thing I overlooked, which is very important, is the fact that it gives off 25.0 joules of heat. So what that means is that Q is negative. So I'm going to put negative here, which means that delta T is going to be negative here as well, because if the ring loses heat, the temperature of the ring is going to drop, all right? So therefore, remember now, the final temperature minus the initial temperature is equal to delta T. So this implies that final temperature the final temperature will be equal to delta T plus the initial temperature, Ti, which would be equal to minus 21.2 degrees Celsius plus the initial temperature. What's the initial temperature? 37.0 degrees Celsius. So, so 37.0 minus 21.2, according to my calculation, that will be equal to 15.8 degrees Celsius. Okay, so that's basically how that is done, all right? All right, so I'm going to stop this video here, and then I'm going to take a break and get to creating another video. So